And really 7/2 n squared, do we really need the 7/2? For accuracy, yes. But the bottom line is, what does n squared tells us? N squared tells us that if the size of the problem is 1,000, we're talking about an order of a million operations. Order of a million means 3 million, 4 million, 5 million, 65 million, 12 million, 13 million, half a million. Those are all order of n squared when n is 1,000. Okay, so we got that part. So now, let's take a look and modify our code slightly. And where's the code modification? Do I have it up here? Yeah, so I'm going to modify line number 2 from j goes to 1 to n minus I. N minus I, whereas before it said n minus 1. What does it mean? It means when I is 1, it's n minus 1. But when I is 2, it's n minus 2. And when I is 3, it's n minus 3. And when I is maximized, it goes in when I is equal to n minus 1. Therefore, j goes from n minus 1 to n minus 1, which is how many iterations? 1. When the upper index and the lower index on a summation or a loop are the same, 1 iteration. Well, if there's 1 iteration, there's 1 comparison, and at most, 1 swap. So that's what we did. We changed that n minus 1 because it's unnecessary to go all the way on the 5th comparison. We really don't need to do the last 5 or the last 4 because they're already set. So it's going to be no, 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 no. So just stop here. Stop at the last possible comparison where it could make a difference. Okay, so we change that, and so what happens is our statements get a little bit different in the sense that the first one is still exactly the same, and the second one really is still exactly the same, pretty much. But 3, 4, 5, 6 now can be lumped together as 1. Why? Because 3 is the test, and 4 is the swap. So therefore, if we're going to test, the worst case is, every single time I compare, I'm going to do a swap. Now, is that really going to happen on average data? No. But nothing worse can happen, so this is the worst case analysis, worst case scenario. And in computer science, we like to be sure that nothing worse than this is going to happen if we run it on real data. So it's a reasonable thing to do to use worst case analysis. So now in this case, so therefore, all of these statements are going to execute n times n minus 1 over 2. So now we're going to add up the n. It's going to go here. This is just n squared plus n over 2. It's going to go here, minus 1. And then here, we're going to have 2 times n squared minus 2. This is going to be n squared minus n over 2. And we're going to just multiply across for the number of statements it has. When we add up all this algebraically, we end up having a quadratic function, which is not the same as the other one, because the other one, the lead term was 7 over 2n squared. This one is 5 over 2n squared. But notice it's still n squared. So therefore, in terms of order of magnitude, it's still, when n is 1,000, this is still millions, just like before. Okay, so it's 3.5 million instead of, it's 2.5 million instead of 3.5 million. It's still a million. Right? So, they are close. So even though we improved our algorithm, it's still not that much different. This is a lower instruction count, but the order of magnitude, same, n squared. This is still one of those n squared algorithms. So if we speed up a computer by 16, we'll only be able to solve a problem how much bigger? 4, because it's the square root of 16. Because if it's quadratic, the inverse is square root, so it's going to be 4. Get it? Okay. So that's what determines the algorithm complexity, the fastest growing term. Everything else gets absorbed into that term. And we really don't too much care about the coefficient, actually. Okay, so now we want to talk about something called the characteristic operation. The characteristic operation in bubble sort is really the comparison. Compare the two elements. The less I compare, the more efficient my algorithm is going to be. For example, imagine that my data was already sorted. Already sorted. So every time I compared, the answer was, no, they're fine. So therefore, I never swapped. Okay, so let's say I kept track of swapping. And I said, okay, number of swaps in this pass. No. Well, if I didn't swap once, what's that mean? my data is already sorted, don't do the second pass because it's going to be more of the same. If you couldn't swap here, I don't think you'll swap here. It's the same stuff, the same comparison. So therefore, it's possible that we can reduce the number of comparisons by simply, if the data is already sorted, we'll do one pass, no swaps, done. What is the function that describes the number of passes, of swaps, of comparisons rather? Is it linear or is it quadratic? In that case. It's linear, because if I have 1,000 elements, I only need 999 comparisons. And if I don't have any swaps, I'm done. But if I have to swap if I need every single pass all the way to 1,000 passes, then I'm going to do 1,000 times 1,000 comparisons, that's n squared. So the worst case is n, in fact, we know that from before, that is the worst case. But the best case is just do one pass, and if you don't do any swaps at all, stop. Or maybe I can do a pass, let's say I kind of swap of 2 or 3. But on the next pass, I don't have any swaps. What should I do? Stop, it's sorted. So it's possible that I may need, now, if the data is sorted, I need one pass. There's no way I can have 0 passes, because how would I know it's sorted? So I need one pass if the data is already sorted. Right? If the data is not sorted, okay, but I don't swap, I swap on the first, but I don't swap on the second, then I only have needed 2. Right? It's possible, if n is 1,000, I may need 3. It's also possible I may need 800. Just one element in a funny spot forces me to do the worst case scenario. For example, if my swapping is going this way, imagine the smallest element, which wants to be here, is here. The smallest element. So what's going to happen? Tick, 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 tick. Smallest. Bloop, one more. Next time around. Bloop. How many times is it going to take for that element, smallest, to go up when I'm swapping this way? It's going to take about n passes. One element causing the worst scenario. How about the second worst scenario? Well, that element could be one higher. Same situation. Or the second element, not the first, but the second, all the way at the bottom. Same scenario. Ah. So, it's not as simple as we thought. So therefore, you can see that it's possible that the bubble sort requires less work, but how do we know about it? In order for us to change that algorithm, we have to actually change the code in the algorithm to be sensitive to the number of swaps in any pass. And that's what we're going to look at the next one. So in the next one, we are going to see that logic added in right here. So now, the pass is 1, the swap is true, while swap is true and pass is less than n minus 1, which is the maximum number of passes. Swap goes to false, and then I do my actual comparisons. If, out of order, swap and set swap to true. But if I'm going and it's always false, always false, always false, then swap is equal to false, it never gets changed to true because there is no swaps. Therefore, when this inner loop finishes and swap is false, the while loop, which forces the next pass, swap is false, and anything goes to false. So therefore, this algorithm will stop early if the data has been sorted already because the last pass did not have any swaps. So the question is this a better algorithm? Yes or no? What do you think? Yes. So everybody thinks it's a better algorithm, but wait a minute. It's only better it's only better if it's always better, or it's only better if it's usually better. Or if it's better more often than not. How could it be worse? Well, I'll tell you how could it be worse. Imagine I have the situation where my little guy is on the bottom. I'm going to require all the passes. Okay, that's the way it is. I'm running this algorithm. Notice that now I have a condition. It's not just counting the passes, but it's actually testing this condition, which is always true. I always have to swap at least once. Always true. And then I have an extra statement, statement number 4. And then I have an extra statement here. So I'm actually executing more statements. So my instruction count, in the worst case, is actually increased. The question is my instruction count in the average case decreased? hard question to answer because what the heck is an average case anyway? What do you mean average case? Average case. Do you mean if you have n elements, n over 2 is the average number of swaps? Well, that's a nice number. We like n over 2. Simple, but that might not be true at all. Do we know how many passes are required to sort the data? And the answer is no, we don't. For example, let's consider one simple example. Let's say we have 10 data elements in our array. 10 data elements, all right? And they are randomly generated, and they're all unique. Make it interesting. They're all unique. The question is, how many permutations, how many orders of those elements can we have? And the answer is 10. 10 factorial. Because I have 10 unique elements, so I have 10 choices for this element. Randomly, 10, 9 this, 8, 7, 6, and it's all, next time I pick the elements, I have 1 out of 10. For the top elements, 1 out of 9, it'll always be different. So it's 10 times 9 down to 1, it's 10 factorial, which is approximately 3.6 million elements. 3.6 million ordering for permutations. Now, we could actually run all those permutations on a computer and count how many swaps were necessary on bubble sorting. And what we will find, which is very interesting, is that we will have 3.6 million permutations, but there are only 9 possible categories into which each permutation belongs. The first category is you did 1 swap, and you sorted. The second one, you did 2 passes, 1 pass, 2 passes, 3, 4, 5, 6, 7, 8, 9. With 10 elements, after you do 9 passes, you're done, guaranteed. Since there are 3.6 million permutations or orders of numbers, all of them will fall into one of those required number of passes, 1 through 9. Now, let's suppose that X of them fell into the 5. X of them, X of the 3.6 million fell into the 5. What does it mean? It means that the probability of requiring 5 passes is X over 10 factorial. If Y of them fell into the 9, that means the probability of having the worst case maximum number of passes is Y over 3.6. So each of those 1 through 9 categories, or I'll call them classes, has a probability. So the probability is the number of permutations that fell into it divided by 3.6 million, which is 10 factorial. So it's going to be the number of them in the ones over 3.6 million, 2, 3, 4, 5, 6, 7, 8, 9. So what is the expected number of passes? We'll take the probability. So we will take the probability. So for example, we'll take the probability. So in the ones category, we're going to have to, let's call it x1, x2, x3, x9. So x1 over 10 factorial is the probability of the data being sorted. Right? x9 over 10 factorial is the probability of requiring 9 passes. x8 over 10 factorial is the probability of requiring 8 passes, etc., etc., etc. How do I compute the average number of passes? Using that algebra. How do I compute the average number of passes? So the average number of passes, I'll put it up here. So the average number, so we're going to have x sub I over 10 factorial. That's the problem. Now remember, x sub I, there's only x sub 1 through x sub 9. And remember what x sub I represents? X sub I represents number of permutations or orders needing I passes. So x of I is comprised of x1, x2, x3, all the way to x9, right? So this is the probability of needing I passes, where I has to be in the range of 1 to 9. We're going to multiply it. We're going to multiply this by 1. This is the probability, right? Probability tells us how likely is it. But we have to multiply the probability by the work given that probability. So for example, if we look at x5 over 10 factorial, that's the probability of a permutation requiring 5 passes, given 10 elements. Right? So suppose I have one of those permutations there. How much work is being done? How much work is this permutation using 10 elements? Using n is equal to 10. N is equal to 10. This is the probability. I'm going to call it PR, probability. We're going to multiply this by the amount of work being done if you do in fact have that. What is the probability, what is the work that you will do if you have 5 elements, 5 passes necessary? Well, so we have to basically, how many times is the outer loop going to go in? How many times is the outer loop going to go into the inner loop? 5 times, because each time it goes into the inner loop, we do a comparison. Okay, so it's going to be, so now what we need to do is we need to 5 times, right? But each time is going to be unique. Because the first time it's going to go what? The first time is going to make all the comparisons, which is going to be n minus 1. So this is going to be times n minus 1. Why n minus 1? That's how many comparisons I'm going to make on the first pass. But on the next one, I'm going to require what? N minus 2, then n minus 3, then n minus 4, I'm going up here, and then finally 1, 2, 3, 4, and then n minus 5. What's the bracket? So the work is the product of n minus 1 to n minus 5. So it will be the summation of the probability, I'm going to call this the probability, times the work, right? And the work will be a product. Do you understand that if I change this 5 to a 4, what's going to change here? If I change this x5, that's not going to change, but if I change x5 to x4, what will change here? I still need to do this, but not that. So my product here will be squeezed down to only 9. Right? How do I show a product? Well, sum shows summations. So the summation is going to go, I is going to go from what to what? We're counting what in here? We're counting what? I is counting what? First of all, how many different scenarios do we have for 10 elements? We could have 1 pass, or at the most 9 passes. So therefore, we're going to count from 1 to 9. So if we count from 1 to 9, if I is equal to 1, then x1 is the number of permutations out of 10 factorial. That's the probability of a random permutation being that one being multiplied by something else. Now, if I is equal to 5, so I is going to go to 2, 3, 4, 5, 6, 7, 8, 9, right? When I goes to 5, it's going to be x5 over 10 factorial times the product, exactly what we had here. And the product we usually write using the Greek letter pi, And pi is going to go from 1 to 5. So j is equal to, we're going to start at 1. What are we going to stop at? I. If we stop at I, and I is equal to 5, 1 to 5, and I is 6, 1 to 6. So that makes sense. So j is going to equal from 1 to I. And what are we going to multiply? We're going to multiply, well, in this case, you can clearly see, it's going to be, now what is equal to n? N is equal to 10. 10 minus j. It's a very complicated looking formula. It's not as complicated as it looks, but it looks complicated. I'm just telling you that right now. So I'm going to put another big fat bracket here. So that's actually the mathematical description of how to find the probability. This is using 10. Now, if our value is not 10, then we can generalize this value quite nicely. Instead of 10, I'm going to put in what? I'm going to change 10, and I'm going to make it an n. And is that red? Really? That doesn't look very red. Okay, but it is, I guess. Okay, so, no, I don't want this. Oh. Okay, this is not red either, but it's much more red than that one is. So, so this is going to erase that. So that n, that 10 is going to become an n. You know, maybe that was red. Maybe I think it's the colors from this thing. That's what it is. Okay, so what else do we change? 10 factorial gets changed too. It now becomes not 10 factorial, it becomes n factorial. And finally, if this is not 10, then we may need not 9 swaps. If it's 100, we might need 99 swaps. So this is going to be 1 less than n, or n minus 1. So that's really the general expression of how we could sort it. This is just an expression. We can't find this. What's the problem with this? Why can't we find this? Because we have to simplify it. We have to get rid of these crazy sigmas and crazy pi's and replace them with some meaningful numbers. So this is a hard problem to solve. I'll give you a clue. The solution is bad. It's not hard. It's hard, but it's not. It's bad, meaning that both sort has a bad. You'll get a bad result here, meaning that you're going to need most of the time, most of the passes, not all the passes. Almost always, the probability is very, very high. The number of passes is going to be very, very high, which means that if you use our last version of the algorithm, the checking for swaps, it's always going to be bad. It's going to be adding extra information. So overall, it may end up being actually a more complicated way to implement. Okay, so that's the basic idea here. You don't have to remember that. I just thought I'd throw it out there because we're going to be getting to that type of thinking. Okay, so this is not for memorization. This is just to show you what you would have to do. Okay, so now we're going to come to what I've been leading up to, and that is how do we find the average behavior of an algorithm? Not the worst case, not the best case, but the average case. Well, in order to do that, why don't we consider all the possible cases? Because the first case we have here is the best case, worst case, and the average case complexity. Huh? That's a miracle. How many times did I have to do that? No answer. Okay. So what I'm talking about is, again, let's remember what the important thing that I mentioned was. And that was when we took this 10-element array and we reordered it in all possible ways, we came up with 3.6 million permutations. But all of them were in class 1 or class 2 or class 3 or class 9. All of them. So we don't care about how many ways the data can be organized or permuted. We care about how many classes do all the data permutations fall into. So that keyword is classes. So an algorithm P accepts k different instances. K instances means are permutations or just different input possibilities. Instances are the actual data, how they're actually ordered. Okay? Now, Ti of n is the time complexity of the algorithm P given the ith instance. where I goes from 1 to k. So Ti of n is how many instructions, or how many proportional to how many instructions will you execute on a problem size A, given that it is the ith instance. Because the ith instance may need more than the ith plus first instance, right? Not all of these terms, this is term, 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 not all these terms are the same. These terms are all a little bit different. So we want, so the best case complexity is take all the Ti of n's over all the instances of the possibilities. You can think of it all the classes, like classes 1 through 9. And pick the one which is the minimum of them across all k classes. Best case scenario. So for bubble sort, we would pick the class 1 pass. We would say, once the data is already ordered, then I will have 1 pass, no swaps, I'm done. Okay, is that realistic? Well, here's how realistic it is. If the data is actually randomly generated, and you have 10 elements, and there are 10 unique elements, then the probability that generated 10 unique elements are ordered immediately is 1 out of 3.6 million. So the answer is it's not very likely. And if the number of elements is 80, it's 1 over 80 factorial. It is so unlikely it's not even funny. So the question is, the best analysis is like, ha ha ha, it's really good, but it's totally unrealistic. Okay, so now it's useful, don't get me wrong, but it's not realistic. So the worst case, we do the same thing. We look at all the Ti of n's across all the classes 1 through k, and we take the maximum, the worst one. So of course, if we did bubble sort, we pick the one with n minus 1 passes. That's the worst case. Is that realistic? No. It's more realistic than the best case. Okay, and finally, here's where things get interesting. The average case complexity is the most interesting because it gives us insight to real behavior, real expected behavior, what we can expect. If we can describe the average case, if we can model it mathematically, then all we need to do for the average case is to go through every one of the cases. By the way, this is what we did down there, it's much more complicated. This is the general approach. We go through every class of problem and we multiply its probability by its work. And that's what we did here. The work happened to be, this would happen to be the work. Because the work was basically a product that depended on I. So how many do you do here? And this is the probability. So you always multiply the probability by some number of factors for the work. But we will find that oftentimes Ti of n is not as complicated as I showed for bubble sort. Okay, so let's take a look at this algorithm called the linear search. And I'll explain to you the algorithm, and then we'll look at this idea. So the algorithm is super, super easy. What we have is we have an array of data. So here's my array of data. And what I'm going to, every element, you can think every element is unique or not, I don't really care. Unique is good. So think of n elements that are all unique. I'm searching for this element. Is it in the array? Is this element in the array? So I check. Yes or no? No. How about here? No. How about here? No. How about here? Yes. Okay, I'm done. So how much work did I do? Compare, 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 compare. No, no, no. Yes. 4 units of work. If I have 1,000 elements and it's not an array, I will do 1,000 units of work, and I will get 1,000 notes. Best case, I'll make 1 comparison, so I'll hit it, 1 unit of work. What's the average you expect? So, this is the algorithm. This is the algorithm that I just explained. So what we're going to do is we're going to look at the probability. Now, we're going to say the data is completely randomly organized, and the probability of finding the element is equally likely anywhere. So if I have n elements in the array, and I'm going to find the element, then the probability is 1 over n, each location. 1 over n, 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 1 over n. What happens when you add up 1 over n times? So you get 1. Now, if the probability is not 100% that you're going to find what you're looking for, but the probability is 50%, then you have 0.5 over n, 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 n times. What happens when you add 0.5 over n, n times? You get 0.5n. So, if the probability is something, but we don't know what it is, then we can, instead of calling it 0.5 or 0.4, because we don't know if that's realistic, we just call it p. P is the probability. We'll say p will be a value which is going to be less than or greater than 0, less than 1. Probability is always a value which is less than or equal to 0, greater than or equal to 0, less than or equal to 1. Probability is always a value between 0 and 1. Cannot be lower than 0, cannot be higher than 1. What happens when it's higher than 1? I don't know. It's not probability. Probability cannot exceed 1. Very rarely does probability ever hit 1. What are we really 100% sure of? Some people are mostly sure or 100% sure that the sun will rise tomorrow. Well, that's a nice thing to believe in. I think it's a very high probability. I wouldn't say it's 100%, it's certain, but I would say it's very, very high, very 0.9, very many more nines to go. Okay, so certainty 1.0 is very unlikely that we are 100% certain of something. I mean, we can believe it, but that may not be realistic, really, for everyone all the time. It's just not going to be realistic. Okay, so you can see that if I am searching for the element and I match it in the first location of array R in position 1, then the probability of that was p over n, and the amount of work it takes is 1 comparison, 1 unit of work. I matched immediately on the first one. Now, if I match it on the second one, that means I did not match on the first one, I matched on the second one, the probability was the same, and the amount of work was 2. Because I mismatched and I matched, so 2 matches. Each comparison is a match. We call that comparison a characteristic operation. Characteristic operation is an operation which is the definitive or the clear, most important part of an algorithm. For bubble sort, it was the compare. Here, it's also the compare, because we're trying to search for something. So if I match it on the ith element, my probability is still the same, because it's equally likely everywhere, and then the amount of work I do is I. So I go from 1 to I. If I match it on the last one, my probability is still the same, and I do n comparisons, and I finally match. I mismatch on n minus 1 match on the last one, and finally I have one more class that's possible. The n plus first class means that x is not even in the array. And if x is not in the array at all from 1 to n, the probability of that is certainty minus p. Because if the probability of the element being in the array is 30%, then the probability that's not in the array is 70%, which is 1 minus 30. So the probability of